Hello and welcome. Thanks for joining me. You are going to learn about practical text classification with Python and Keras. My name is Douglas Starnes, and I'll be your guide for the next half hour. This course is about natural language processing, or NLP. The field of natural language processing studies how computers can parse and extract information from natural language. This is a big field, so in this course, you'll focus on a single task often used in NLP, sentiment analysis. The goal of sentiment analysis is to predict the mood of a body of text. For example, the text, "That was the worst movie I've ever seen," would have a pessimistic or negative sentiment. The phrase, "I want to watch that movie again. It was fantastic," would have an optimistic or positive sentiment. The course will begin with some simple examples using scikit-learn, and then it will get more advanced and close with building convolutional neural networks. Let's get started in the next video. I've set up a Jupyter Notebook on Google Colab, a free service for editing and hosting Jupyter Notebooks. I'll be referring to it throughout the course. You can follow along by cloning the notebook located at the URL at the bottom of the screen. Using Google Colab is done for your convenience. If you like, you can still download the notebook and run it on other services like Microsoft Azure or locally using a stock Jupyter Notebook server. The advantage of Google Colab is that all of the packages needed to complete the demo are pre-installed. And to get started, you just need to connect to a runtime hosted on Google servers with a single click. Before starting any data science or machine learning project, you should fully understand the data you are working with. This course will use the sentiment-labeled sentences dataset from the machine learning repository located at the University of California, Irvine. You won't need to labor over the function getData. It simply uses modules from the Python standard library to download the dataset zip file, save it to disk, and then the extractData function to extract it. At this point, you can open the Files tab in Google Colab and see a folder named Sentiment-Labeled Sentences, which is the contents of the dataset zip file. Note that the free tier of Google Colab is a shared service. If your session times out and the resources are reclaimed, you will lose any files that you downloaded. In this case, it's not that big of a deal because you just download them again. But if you save any data generated by your notebook, it's a good idea to download it. The next function, Rename Data Folder, cleans up the folder names to make the code more readable. Open the file Amazon Cells labeled.txt and look at the contents. Each line has a sentence and then a sentiment score. For negative sentiment, the score is 0, while positive sentiment has a 1 score. And there are two other files for data from the Internet Movie Database and Yelp with the same structure. You're going to concatenate those files using pandas. First, import pandas and alias it as PD because data scientists don't like to type. Next, create a mapping between each file in the dataset and its source. Iterate over the files in the dictionary and read each one into a pandas data frame. Notice that even though you are using the readCSV function from pandas, you can specify any separator. The files in the dataset are tab separated, so use the SEP keyword argument to tell pandas to use the tab character instead. And the names keyword argument contains the names of the columns to be used in the data frame. Keep the source of each item by appending a new source column to the data frame. Then store each data frame in a list and join them together. Using the head method of the data frame, we'll show the first 5 items. In the next video, you'll start to prepare the data for machine learning. This video starts off with some terminology. In the previous video, you combined the data from 3 sources, Yelp, Amazon, and IMDb, into a data frame. The data frame contains sentences, labels, and sources. The sentences are a collection of texts that you will use scikit-learn and later Keras to make predictions. This collection of texts is referred to as a corpus. If you drill down to the word level, the collection of unique words in the corpus is called the vocabulary. The reason why you use only the unique words is because each one will be assigned a unique index that will be used to identify the words during training. Machine learning algorithms don't like text, so we have to represent the text with numerical values. If you take each sentence in the corpus and convert it into a list of numbers using the indexes mapped into vocabulary, you get a feature vector. This is a numerical representation of each sentence. Let's see how this works in more detail. The next cell in the notebook defines 2 sentences. You're not going to train a model using these sentences because there aren't enough of them, but you'll use the classes inside of scikit-learn to explore this concept of converting a corpus into feature vectors. In the next cell, import the countVectorizer class from the sklearn.featureextraction.text module. Get a vectorizer which will consider all words, regardless of the frequency or the number of times they appear, and that is case sensitive. Tell the vectorizer to create the vocabulary from the sentences by calling the fit method and passing it the sentences. The vocabulary is found in the vocabulary underscore field. The vocabulary is a dictionary with the unique words as the keys and the indexes as the values. To get the vectors, call the transform method on the vectorizer and pass it the corpus, the sentences. This will return a sparse matrix from the SciPy module. Use the toArray method to display the vectors. Notice the structure of the vectors. The vectors are the same length as the vocabulary. For each sentence, a new vector is created, and for each word in the sentence, the index of the word is a 1 in the same index in the vector. For example, the first sentence is John likes ice cream, which is indexes 0, 5, 4, and 2. And the first vector has a 1 at indexes 0, 2, 4, and 5. A sparse matrix is a good choice when you have a matrix with a lot of unused values. Your vocabulary right now only has a half dozen words, so this might not be obvious, but later on you'll work with a larger vocabulary of over 1,000 words. It's unlikely that even 5% of these words will be used in a single sentence. The number of unused words in each sentence will be quite large. You can reduce the size of the matrix by compressing that unused data and focusing only on the relevant data, and this is what a sparse matrix does. You've just created what is called a bag of words model. In the next video, you'll use this model to train a machine learning model using scikit-learn. While training a machine learning model, you'll often split your dataset into two parts. The first part will be used to train the model, and the model is used to make predictions from new data. However, during training, your model will see the training dataset over and over many times. It's possible that the model could get very comfortable with the training data and perform very well with it. However, when it sees new data outside of the training data, it might perform poorly. And this is a phenomenon known as overfitting. In other words, the model is fit too closely to the training data, and this is contrary to the goal of a generalized model that performs well on any data. One way to prevent or detect overfitting is to use the remaining part of the dataset for testing, and this will give the model a chance to see data not in the training dataset, and then you can evaluate the performance of the model. Let's take a look. You're going to focus only on the Yelp data for this experiment. Use pandas to filter the data frame and return only those items that have a source of Yelp. Next, get the sentences and labels from the data frame. The values field will extract the values of the columns into a NumPy array. Performing the split is not as straightforward as you might expect. One potential issue is that the labels might not be evenly distributed across the training and testing datasets. If you train the model on a dataset that is mostly positive sentiment, and then test it on a dataset that is mostly negative sentiment, you're not going to be impressed with the outcome. In the module sklearn.modelSelection is the train test split function. This will create the training and testing datasets for you. First, import the function. Then call the function, providing the sentences and labels, along with a percentage of the data to be used for the test dataset. Here you'll use 25%. You'll find that there are a number of religious debates about the ideal split point, but usually it's going to be around 20 to 30%. In this case, for reproducibility, specify a random state of 1000. The function will return 4 values: the sentences in the training dataset, the sentences in the test dataset, the labels in the training dataset, and the labels in the test dataset. The next cell repeats the process you saw in the previous video to vectorize the sentences. Notice the size of the sparse matrix. The vocabulary is 1,714 words, and there are 1,000 sentences in the Yelp data, so 75% would be 750. Therefore, uncompressed, this would be 750 vectors of length 1,714. And this is a total of just under 1.3 million values. Now, how many sentences can you think of with 1,700 words? Or, for that matter, even 170 words? Well, it turns out the average length of a sentence in the dataset is about 11 words, and the longest sentence is 32 words in length. Now you should be able to see this value of the sparse matrix. It's time to do some machine learning. You're going to use an algorithm called logistic regression. Without going too deep into the mathematics, the result of logistic regression will be a value between 0 and 1 inclusive. If you consider the lower values between 0 and 1 to be negative sentiment and the rest to be positive, logistic regression can be used for binary classification. And that's all the math you need to know because scikit-learn provides a logistic regression class. Import the logistic regression class from the sklearn.linearModel module. Then create a new instance. and use the fit method to train a model on the training data. Then use the score method to test the model. And the model is about 80% accurate. Before training the model on the entire dataset, I want to call attention to the amount of code written to prepare the data versus the amount of code written to train the data. Even if you leave out the vectorization experiment, which is only about half a dozen lines, you wrote a lot more code to prepare the data. And this validates a common feature of machine learning. Up to 80% of your time is spent preparing your data. Because garbage in, garbage out. You may find that you're not spending as much time as you expected writing code for actually machine learning. Now, I'm not going to labor over the next piece of code because there is not really that much new. All it does is repeat the logistic regression on each source in the dataset and print the score. You'll see at the Amazon dataset the score is similar to Yelp, and IMDb is a little worse, but not terrible. Now that you understand the process of sentiment analysis, in the next video, you're going to see neural networks for the first time. Neural networks. We're going to build a brain out of Python. Actually, that's a valid statement, but it depends on the definition of brain. If it refers to the human brain, nothing could be further from the truth. The word neural invokes visions of the nervous system, and as the CEO of the nervous system, the brain is often associated with neural networks. But neural networks are loosely inspired by how neuroscientists think the brain might possibly work, and that's assuming that they are on the right track. TLDR, we cannot reliably replicate the functions of a human brain in Python or any other language, and that's because we don't know enough about how the human brain works. But on the other hand, neural networks can still be quite useful for certain tasks. For example, a common job for a neural network is the convolutional neural network, or CNN, that you will implement later in the course. Neural networks are used in classification, regression, generative models, computer vision, voice recognition, and you will get hands-on with neural networks and natural language processing. The loose inspiration for neural networks is based upon the structure of neurons in the human brain and how neurons are connected to each other, thus forming neural networks. Here's a picture of a very simple neural network, and it's likely you've seen a similar one. The circles represent the neurons or nodes, and the lines are the connections between them. Notice that the nodes are organized into layers, and this particular network has 3 layers. The first layer is creatively referred to as the input layer, and this is the layer which receives input in the form of feature vectors for your NLP project. The output layer returns the predictions. In between are 0 or more intermediate or hidden layers. They are called hidden because we don't touch them, unlike the input and output layers. A deep neural network is one with more than 2 hidden layers. At the risk of getting mathematical, here is the formula for calculating the output of any single layer. Most of the value is a sum of products. Each input value A is multiplied by a weight W and summed with B, the bias. This alone is enough to compute values in a neural network. However, there is a limitation. Notice that the weight times the input plus the bias is a linear function. So at this point, a neural network could only train models representing or approximating linear functions. The real world is much messier than straight lines, so the goal is to be able to train a model approximating any arbitrary function. Thus, neural networks are often referred to as universal function approximators. To introduce nonlinearity, you use an activation function f before calculating the final output. A common activation function for hidden layers is ReLU, or the rectified linear unit. It's essentially the linear function with negative values adjusted to 0. The sigmoid function, which squashes values to between 0 and 1, is often used as the output layer for binary classification. Sentiment analysis is a form of binary classification. It's obvious that the values of the weights and bias influence the predictions. The weights and bias are known as trainable parameters. That's because, during training, the weights and bias are continuously updated. The initial values are random, and thus the first prediction for the first feature vector is going to be terribly off. However, the prediction and actual label will be given to a cost or loss function. This measure of similarity will calculate how good or how bad the prediction was and send the result to an optimizer. And the optimizer will adjust the trainable parameters in the model with the goal of better predictions in the future. When the optimizer updates the trainable parameters, it completes a loop that starts over with the input layer receiving the next feature vector in the dataset. And this is called backpropagation. And this loop of updating the trainable parameters is what makes neural networks useful. Again, you don't need to know the math used to make the loss function or the optimizer, but it's good to be familiar with the steps. In the next video, you'll see how to use Keras to realize those steps in code. Before building the neural network in Keras, reconstruct the training and test datasets using the Yelp source. You might not have heard of Keras, but you have probably heard of TensorFlow. Originally, Keras was a wrapper around the lower-level API of TensorFlow and also worked with several other backends. Today, in TensorFlow 2.0, Keras is part of TensorFlow. Many of the APIs are still the same, you just get to them through the TensorFlow modules. TensorFlow 2.0 is pre-installed with Google Colab, so all you need to do to start using it is import Keras from the appropriate modules. Recall that in the previous video, you saw models, which are composed of layers. Keras represents the model and layers as objects in the Keras modules. So you'll create a model, and then you'll add layers to it. The type of model you'll create is a sequential model. Its name implies a sequence, in this case of layers. And that's exactly what you'll do. Create a sequence of layers, starting with the input layer. First, create a sequential model. Then call the add method and create a new dense layer. A dense layer, also referred to as a fully connected layer, receives every output from the previous layer and sends those to every input, except for, of course, the input layer. The layer has a size or number of units, 10 in this case. So this layer will have 10 values. Don't worry about where the number 10 comes from, just focus on the higher level concepts. Since this is the first layer, you'll need to provide the number of inputs for the layer to expect from the vectors. Recall the training data for the Yelp data source has 750 vectors, each of length 1714. The size of the input layer will be the same as the length of the vectors. Set the input_dim keyword argument to the second value in the shape of the training data. And finally, set the activation keyword argument to ReLU. Next, add another dense layer for the output layer. The size of the layer is 1, and the activation function is sigmoid. Call the summary method on the model to see an overview of the layers. The total number of trainable parameters is 17,161. Now, where do these numbers come from? Recall that there are 10 nodes in the first layer times the 1,714 values in the input layer for a total of 17,140, plus the 10 bias values for a total of 17,150. The second layer receives the output of the previous layer, which is 10 values, plus the single value in the layer for a total of 11. So that means there's going to be 17,161 values for the entire model. The next step is to call the compile method on the model, and this is where you will set the loss function and optimizer. Use the loss keyword argument to set the loss function to binary cross entropy, and the optimizer keyword argument to set the optimizer to atom. Again, don't worry about where these values come from, just focus on the high-level steps. The remaining keyword argument metrics is a convenience in Keras that collects statistics during the training process. At last, you can train the model. Call the fit method on the model. This method accepts the training vectors and labels. There are a number of keyword arguments that represent hyperparameters, such as epochs. An epoch is a complete iteration through the training data. Recall that the first predictions are going to be rather poor until the model begins to zero in on the correct weights. After the first iteration through the training data, the model deserves a second chance at improving those poor predictions, and a third, and a fourth. In this example, it'll get 100 chances. Now, epochs is a hyperparameter because it is a non-trainable value. You set it, and it doesn't change while training. Also, you can use the testing data set as validation data to watch the accuracy of the dataset improve while training. Execute this cell, and enjoy the show. Actually, things happen rather fast with this dataset. But notice that while the model was training, the loss decreased, and the accuracy increased. The validation loss started to increase about halfway through training, and that could mean that the model started to overfit. More on this in a second. However, the accuracy overall is still better than when it started. To test the model, call the evaluate method. First test on the training data, and then on the test data. The evaluate method returns the loss and accuracy scores, but you'll just use the accuracy in this experiment. Notice that the training accuracy is 100%, but the testing accuracy is just under 80%. This adds to the argument that the model overfitted, as it performs much better on the dataset used to train it, but not so well on new data. You can see the results of overfitting using this little function called plot history. Recall that you saved the return value of the fit method when training the model. The return value has a history property, which is a dictionary with keys for the training accuracy and loss, and the validation accuracy and loss at the end of each epoch. There were 100 epochs, so you'll have 100 values for each. Pass the history object to the plot history function, and you'll get these graphs. Notice that the training accuracy reaches 100% long before the 100th epoch, and that the validation loss begins to increase about the same time the training accuracy reaches 100%. Therefore, there is no reason to train this model more than about 25 or 30 epochs. More training is not always the way to an accurate model. Note that this is a very small data set, a few thousand operations, and real-world data sets would be millions or even billions of observations, so this example does not really require a neural network. In fact, you could get better results without a neural network because neural networks are better suited for very large amounts of data. The smaller data set also has another disadvantage when it comes to testing and validation. In this example, they are the same, but in the real world, you would partition your data set into training, testing, and validation data sets. However, you are making the trade-off to work with a model that doesn't take hours to train. There is more than one way to represent a corpus. In the next video, you will see an alternative method to the bag of words model. Let's take a look at another way to represent the words. You've seen the bag of words model that represents a sequence of words as a vector. However, next you'll see how to represent each word as a vector. One way to represent a word as a vector is with one-hot encoding. Take a look at the following code. It simply creates a list of strings. The label encoder from scikit-learn will create a unique integer value for each member of the list. And you do this by calling the fitTransform method. So it assigns 0 to Berlin, 1 to London, and 2 to New York. You can use this to create one-hot encodings for each string with the one-hot encoder in scikit-learn. Notice that the one-hot encoder needs the labels to be in a column, not in a row. And the result is a NumPy array. Again, there's an entry for each string or label. This time, the labels are represented as a vector. The vector is the same length as the vocabulary, 3 in this sample. In a vector, all the values are 0, except for a single 1 value. The position of the 1 value is the same as the unique value assigned to the label. But this is not the ideal representation for text unless you are dealing with categorical values. Next, you'll look at the concept of an embedding layer for more efficient representations of text. The text needs to be prepared, again, up to 80% of machine learning is data preparation, to work with the embeddings. The tokenizer utility inside of Keras will help you convert the text into integer values. The tokenizer will assign an integer value to the 5,000 most frequently used words in the corpus. It will then create a vector for each sentence in the dataset. As you can see, the word "the" was assigned 1, as it is occurring most often in the dataset. So how is this different from using the count vectorizer from scikit-learn that you saw earlier? Recall that the count vectorizer created vectors that were the size of the vocabulary. The tokenizer generates vectors that are the length of each text. This means that the vectors are going to be of different lengths and need to be padded with zeros to make them uniform. It doesn't matter if you pad the beginning or end as long as you are consistent. In Keras, the pad sequences function will take care of padding for you. Give it the text to pad, where to pad, post will pad at the end of the text, and the maximum length of the padded sequences. To create the embedding layer, you can use a pre-trained model. You'll do that later, but first, you'll train a custom layer, and Keras provides more utility classes to help out. Create a new sequential model and add an embedding layer. The keyword arguments for the embedding layer will be the size of the vocabulary, the size of the vectors, and the length of each padded vector. Then send the output to an intermediate dense layer of size 10 and activation of ReLU, and finally the output layer with the size and activation sigmoid. Notice that the output of the embedding layer must be flattened before the dense layer can use it. Compile the model with the same hyperparameters as before. The loss function will be binary cross entropy, the optimizer will be atom, and accuracy for the metrics. Train the model with the fit method like you did before. This time use only 20 epochs. You can see that the accuracy for training and validation are quite low. Test the model and graph the history. Again, the accuracy is too low and the errors are too high. So let's look at a better way to train this model. The problem is that you want to consider the order of the values in the vectors instead of each individual value alone. And one way to handle this is to use a pooling layer. In this case, you'll add a global pooling layer after the embedding layer in the model. Inside of the pooling layer, the maximum values of all values in each dimension will be selected. There are also average pooling layers as well. The max pooling layer will highlight large values. Add the global max pool 1D layer to the model and train it again. Now this is much more accurate, but training a real-world embedding layer would take a lot more time and attention. In the next video, you'll see how to save time by using a pre-trained word embedding. There are many pre-trained embedding layers available to include with your project. Some popular pre-trained embeddings include the Word2Vec from Google and the Glove from the NLP team at Stanford University. In this course, you'll use Glove for its size and speed. Word2Vec is larger, but it is also more accurate, so you can try it once you sync Glove in your code. The next snippet will download the Glove dataset and extract it using utility methods from earlier in the course. It's trained on 6 billion words, so the file size is over 800 megabytes and will take a while to process. I'll speed it up through the magic of video. The file contains a list of words with the embedding vector for that word. Use the next code to get a reduced version of the embedding matrix. The embedding matrix is stored in an array with 1747 rows, which is the length of the vocabulary, and 50 columns, which is the size of the embedding. Before using this matrix in a model, take a look at the number of non-zero elements it contains. There's a little more than 95% of the vocabulary that is contained by the matrix. To use the matrix in the model, assign the embedding matrix to the weights keyword argument of the layer. Also, set the trainable keyword argument to false. The matrix has already been trained, so you don't need to do anything else for it to work. Train the model, test it, and look at the results. And this is better. Can you get more by training the embedding layer more? Let's see. Set the trainable keyword argument to true. Then train and test the model once more and plot the results. You're getting there. Again, this model needs to be trained no more than 20 epochs. In the next video, you'll see an advanced type of neural network which can yield even better inferences. A better approach might be to utilize a special type of neural network known as a convolutional neural network, or CNN. While CNNs are generally used for image classification and computer vision, they are also handy for text processing, as both image and text data involve sequences. A CNN is distinguished from the neural networks you have built by the addition of a convolutional layer. Inside of the convolutional layer, a filter or kernel analyzes the data in pieces, while still maintaining the spatial relationship between the data. In images, these filters are two-dimensional, but with text, you only need a one-dimensional convolutional layer. Here's an illustration of a convolutional layer in action. Your text will be the input features, and the filter will be applied to the first group of features. The output will be stored in a convolution. The filter will slide a predetermined distance to the next group of features and produce an output. Notice that the groups are overlapping. And that's all you really need to know about how convolutional layers work, because Keras abstracts the math for you. Add a conv1d layer right before the pooling layer. Set the number of filters to 128 and the size of the filter to 5, and then set the activation function to ReLU. Notice that the embedding layer is no longer using the glove matrix. The rest of the process is unchanged, so train the model and test it. You'll see that 80% is about the best it can do. Keep in mind that this is a small dataset, and that neural networks perform better with large datasets. However, there is one more technique that you can employ to improve performance. You've actually already been exposed to this technique, called hyperparameter optimization, but without the optimization. To review, most of the emphasis so far has been on training the weights of the model. You've seen those values are changed through the training process. But there are also values such as the vector length and the embedding size that are set before training. These values that are not trained are called hyperparameters, and they still have a lot of influence on the performance of the model. Optimizing these values yourself is impractical, so you can ask Keras for help. Keras will try different combinations of hyperparameters and tell you the best one. For this course, you'll see how to use the scikit-learn utility, randomized search CV, in addition to k-fold cross-validation, to find the best set of values for the hyperparameters. K-fold cross-validation partitions the data into chunks. The number of chunks is the value of k. Here you can see an example of 5-fold cross-validation. On each iteration, a different chunk or fold will be used for testing, with the remainder used for training. So the iterations will use different combinations of training and testing data. Specifically, you'll use a grid search, which maintains the combinations of the parameters. The grid is defined as a dictionary as seen here. The parameters in the search will be the number of filters in the convolutional layer, the size of the kernel or window, the size of the vocabulary, the number of embedding dimensions, and the maximum length of the feature vectors or sentences. To implement the search, the randomized search CV class requires an instance of Keras classifier, which wraps the model in a scikit-learn wrapper. Since the randomized search CV class is from scikit-learn, Keras classifier is an adapter. This class requires the model be returned from a function. You've seen all the code in this function, so I won't go over it again. You've also seen a vast majority of the training code. The first difference is the instance of the Keras classifier that wraps the model, and this is where you set the keyword arguments that were provided to the fit method of the model in the previous exercises. The randomized search CV class accepts the Keras classifier and the grid. The CV keyword argument is the number of folds, or the K value. Finally, call fit on the randomized search CV to start the heavy lifting. The return value from fit will include the best score and the parameters producing that score so you can examine them. This can take a little while, so again, I'll speed it up to the magic of video. Also, if you run this on Google Colab, you'll have access to free GPUs for jobs up to 12 hours. These GPUs aren't the fastest, but they will accelerate this code and take much less time. The final output is stored in a file that I've opened on the right side. A better approach, but still not much more than 80%. A logical conclusion is that a larger dataset would yield better results. Again, convolutional neural networks and neural networks in general are intended for large datasets. Let's wrap up this course and review what you saw. This course was about natural language processing. You saw several techniques for using sentiment analysis. First, you learned about the bag of words model and used scikit-learn to create a baseline model. Next, you learned about logistic regression and eventually used Keras to train a model with a neural network. Finally, you saw the more advanced convolutional neural network and used hyperparameter optimization to find the best values for the hyperparameters. But this is not the end of the story. You could look at another type of neural network called the recurrent neural network. Take a look at the long short-term memory or gated recurrent unit if you are interested. Also, you have not reached the limits of natural language processing. The most popular application is sentiment analysis, but you could also detect spam emails and classify documents and more exciting tasks. If you are interested, there are several good resources to help you dive deeper into this topic. First, you can experiment with the examples on the official Keras site, keras.io. To get more on GloVe, you can read the paper on the Stanford University site. And more about Word2Vec, the pre-trained embedding from Google, is also available. Finally, don't forget the demo notebook is available here. There is also more related content on RealPython. You could extend the concepts of streaming Twitter data for sentiment analysis using Elasticsearch and Kibana, or you could implement speech recognition. And you can always join the Slack community to chat with others. Thanks for watching this course. I hope you found it of use.